Hello everyone, welcome to the Material Science class MIC 300. This is the fourth video of chapter 3. In chapter 3 we are discussing the structure of crystalline solids. Over the last video we discussed the crystal system and the crystallographic points and directions. Today in today's video we are going to discuss the crystallographic planes. How we can define a plane that would include a set of atoms. Depending on the crystal system, this is what will be covered over today's video. So in the crystal or inside the unit cell of any crystal, there should be a group of atoms. This group of atoms would form like a virtual plane. How we can define these different planes for these different unit systems, this is what we are going to discuss over this video. So crystallographic planes are of all crystal systems except the hexagonal crystal systems are represented by three Miller indices, and these indices are arranged as H, K, L. So these are the indices. The H here is an index which is conjugate to the x-axis. The K here is another index which is related or conjugate to the y-axis. The L here is related to the z-axis. And all of them should be enclosed or confined in a circular parenthesis, not a square bracket. If you confine the indices in a square bracket, this gives a crystallographic direction as we discussed over the last video. But a crystallographic plane, you should identify the indices known as Miller indices, and then you're going to confine them into a circular parenthesis or a circular bracket. Make sense? So all the unit systems, all crystal systems, we are using three Miller indices except the hexagonal one. The hexagonal one we have to use. We should use four index instead of using three index or indices to specify the crystallographic plane for a hexagonal crystal system. Why so? This is very similar to what we discussed over the last meeting because of the equivalency that should be achieved between the different directions and the different crystallographic planes. We said that there is a challenge, there is a problem if we decided to use three index notation to describe the crystallographic direction for a hexagonal crystal. Probably this would lead to some of the direction that they should be equivalent, they're gonna have different indices. So we're gonna find a challenge or a problem of identifying the equivalent direct crystallographic direction for a hexagonal crystal system. So that's why we replaced the three index system the three index system by a four index system. We're gonna do the same for the crystallographic plane. We still have the same challenge as will be discussed with more detail. So first, I'm going to explain how we can define the Miller indices, the three Miller indices for all the crystal systems except the hexagonal crystal system. Then I will explain how we can do it for a hexagonal crystal system or a hexagonal crystal structure. Make sense? So this is the procedure that I'm going to go over it very quick. Then I'm going to explain some examples to give more detail about this procedure or more practice. So step 0. What does it mean step 0? It means that this step, it is not applicable in all cases. It is like a test. You're going to apply this step under certain condition. It means that it is not an essential step, but anyway you have to do it. This is the step 0. You have to check if there is a condition here. If this condition exists or this something exists, it means that you have to apply this step. If not, you're gonna skip this step and move directly to step number 1. Make sense? So that's why it had been given step 0 name. So in step 0, if the plane passes through the origin of the unit cell, just to give you more detail, let us assume that you do have a unit cell like this one, and this highlighted thing, this is a plane that could include set of atoms. And we are for some reason interested to specify this plane, to give a name to this plane. So this is what does it mean to specify or determine the Miller indices for a crystallographic plane. So this is a plane which is a virtual plane joined inside this unit cell. And for some reason we would like to give it a name. To give a name, it means that you need to specify the indices for this plane, as we did for the points and the directions. So if you don't have a plane like this one, as you can see, this plane, it intersects with the origin. This point O, this is the 0, 0, 0 point for this coordinate system, for this X, Y, Z coordinate system of this unit cell. This is the origin of this unit cell as you assumed. I assumed this one, I assumed this is the X, this is the Y, this is the Z, and this is the 0, 0, 0 point, which is the origin point. This plane, it intersects with this origin point. It means that you have to apply step 0. So step 0, you're going to apply it under one condition. What is this condition is? This condition that this plane that you are interested in finding its Miller indices, it do intersect with the origin of the coordinate system that is given for this unit cell. So if the plane passes through or intersect with the origin of the unit cell, you do have two options. The first option to draw, you have to draw another plane that is parallel to the original given plane but in the same unit cell, and that is not passing through the origin. This is one method, this is one approach of fixing this problem. We will not be able to apply the next steps as long as this plane is do intersect with the origin. Because the next step depends on the intersection with the axes, and if this plane is, if it intersects with the origin of this X, Y, Z coordinate system, you will not be able to identify these intercepts. So the first step, or step 0, in case that you have this case, you have either the first approach or the first method to fix this problem, to get rid of this intersection with the origin point. You can draw another plane that is parallel. This is the condition, that it should be parallel to the original given plane, but in the same unit cell. And in that case, this new plane that you draw, it will not be passing through the origin point. This is one method. The other method is to construct another neighbor unit cell. Draw the next unit cell, and then you're going to start to investigate the plane and find the indices based on the new unit cell, as already have been done in the textbook here. Like, for example, this is what is given. This is the original plane. So the plane, it do intersect with the 0 point. It do intersect with the origin point. So what happened here, that we draw another unit cell. This is the new unit cell. This is the new, and this is the given one. This is the given unit cell. We cancelled this original unit cell, but we didn't move the plane. We still have the same plane. We just draw a new unit cell, which is next to it. And then we are going to investigate. We are going to apply the other 4 steps. Step 1, 2, and 3, and 4, based on the new unit cell, not the original one. Why not the original one? Because the plane do intersect with the origin. So we had to apply step 0. So in step 0, to fix this issue, this problem, so you could able to apply the other step. This is what you have to do. You're going to do either one of the two options, either to draw a new plane, which is parallel. For example, I can do the same issue by drawing another plane here that is parallel to the original plane, but it will not be intersecting to the origin point. Then I'm going to investigate or apply the other step over the new plane. This is one method. This is method 1. Method 2 is to draw. Keep the plane as it is. Don't move the plane or draw another plane, but instead draw a new unit cell. Make sense? So these are the two approaches as already represented in the textbook. I'm going to give you a very shortcut way. A very shortcut that you can fix this issue or apply this step right away. Instead of drawing a new plane or drawing a new or construct a new unit cell that would be complicated for some of you, the easiest way or the easiest approach, simply you are required to move the origin. For example, in the first method, we are moving the plane itself, right? We are drawing another plane that is parallel to the original plane, and we cancel this one. And then we're going to work over the new plane. So it means that it looks like we have moved the plane to another place to investigate and find its Miller indices. Make sense? So this is for the first step or the first approach. The second approach, instead of moving the plane, we move the unit cell. We move the unit cell itself. So I'm going to give you a third approach, which is much more efficient and better and more simple than these two approaches even. Instead of moving the plane or the unit cell, move the origin point. The problem is that the origin point at its location, it do intersect with the plane, right? So I'm gonna move the origin point at any other point. I do have within this unit cell so many corners. I do have this corner, this corner, this corner, this corner, this corner. So the origin was given to me at this corner that is already clearly intersect with the plane. No problem. No problem. You can move it. You can move this origin at any other corner. Then you're gonna investigate and apply the other steps. You're gonna end up with the same Miller indices if you move the plane or move the unit cell. So these give three approaches. Now you have three approaches. Either to draw another plane that is parallel to the original plane. It means that you should move the plane to another place, but it should be parallel. In the meanwhile, it shouldn't be intersect with the origin. The other approach, or the second method, just to construct or to draw another unit cell and start to apply the other step based on the new unit cell. It means that you like kind of move the unit cell, and you just leave the plane as it is, but moved the unit cell. The third approach, and this is what I highly suggest to you, simply shortcut, move the origin point to any other corner. But the condition is when you try to move the origin, you have to move the axes as well. So what does it mean? For example, I'm gonna move this point O, it do intersect with the plane. Okay, so I'm gonna move it here. I'm gonna assume this is the new O. And in that case, you have to move the axes. So to move the origin point, the y-axis will not be moved because you're still over the y-axis, but instead you're just gonna move the z-axis. So you're gonna have a new z-axis here. And this is gonna be the new x-axis. Make sense? And then you're gonna cancel the original x and the original y. And in that case, you're gonna have the new y, which is still be the same as the previous y. And this is the new origin point, and this is the new z, and this is the new x. And in that case, you're gonna start and go ahead to investigate the intercept for this plane to find its Miller indices. It means that you're gonna apply the other steps. Make sense? So this is the third approach that I highly suggest that you can use for the step 0. In step 1, your objective then is just to find all axes that intersect with the plane. So if I decided to apply the new method, which the new method, it works like you already kind of draw a new unit cell. Because in the new unit cell, this is the new origin, which is typically the same as I've done here. Make sense? Anyway, so if I ask you this plane, according to the new coordinate system, the new axes x, y, z, this plane, it do intersect with which axes? This is the step 2. Step 1, I'm sorry, is just to find the axes who are intersecting, which are intersecting with the plane. So which axes? These axes. It is clearly seen that the plane, it do intersect with the z-axis at a point, right? So it do intersect with the z-axis, let's say at this point, let us give it this mark, this point. So the plane, it is clearly that it do intersect with the z-axis at this point. So this is, it means that z-axis intersects with the plane. This is one axis. How about the y-axis? Do you think that the y-axis intersects with the plane? Yes, it do intersect. Why? Because you should understand that the y-axis, it is extended in the positive direction up to positive infinity, and in the negative direction up to negative infinity. Y-axis, it is entirely extended. So if you try to extend the y-axis, the extension of the y-axis will do intersect with the plane at this point, the previous original point. But I don't care. But anyway, there is an intersection between the plane and the y-axis. So it means that this plane, it do intersect with z-axis and y-axis so far. How about x-axis? Do you think that this plane, it do intersect with the x-axis, the new x-axis? Forget about the previous one. The new axis, x-axis, this new one, does the plane intersect with the new x-axis? No. Why? Because as clearly seen here, this is the x-axis and this is the plane. If you try to extend the plane in the negative x direction, up to infinity, and even in the positive x direction up to infinity, the same thing for the x-axis, negative and positive infinity, the axis and the plane, they will not be intersecting at all. It works in this way. Like you do have a plane, this is the plane that you have, this is the plane, and this is the x-axis. Both are parallel. Extend the plane as much as you can in the two directions. Extend the x-axis as much as you can in the two directions. Both, they will not be intersecting at all. What is the reason? The reason that this plane, it is parallel to the x-axis. So this is for step 1 and 2. So in step 1, your objective is just to specify which axes that do intersect with the plane. This is for step 1. Then, once you identify these axes, find the intercept. From mathematics, the intercept, this is the point of intersection between two axes or a plane and axis. So this is the intercept. It's just to find the intercepts of the plane with these axes in terms of the lattice parameter A, B, and C. Like for example, if I ask you what is this plane, it do intersect with the z-axis at this point. This point, it is half of C. Why C? Because the C, this is, as we agreed the last video, C, this is the edge that is parallel to the z-axis. It means that this plane, it do intersect with the z-axis at a point. This point is C over 2. This C over 2, this is the intercept. So it means that the intercept of the plane with the z-axis, it is C over 2, as already given here. So we got this C over 2. Do the same for the other axis. The plane, we agreed that it do intersect with the y-axis at this point. But it is clearly seen that the intersection point, it is somehow found in the negative side of the y-axis. Because now we moved the origin into new place. This is the new origin point. I moved the origin point. I moved the 0 point. It means that this plane, it do intersect with the y-axis in the negative side. How much is this distance from the 0 to the negative? It is negative b, right? Because this side, it is b, which is parallel to the y-axis. So it means that this distance or the intercept of the plane with the y-axis, it is negative 1b, or it is negative b. And this is for step 1. So step 1 is just to allocate the axes who are intersecting with the plane. Then your objective is just to define the intercepts of the plane with these axes in terms of the lattice parameter A, B, or C. Then step 2, your objective is just to find whatever the plane is parallel to any axis or not. If the plane is parallel to any axis, you're gonna identify or put the intercepts with this axis infinity. And this is the case where the plane, it is parallel to the x-axis. It is not intersecting. Both, this is the plane and this is the x-axis. Both are parallel. There is no intersection between them. It means that, you're gonna add for this x-axis, the intercept of the plane with the x-axis, it should be infinity. Infinity, it means that there is no intersection. Make sense? So this is for step 1 and step 2. Step 3, your objective is just to multiply or divide the obtained intercepts by a common number or a common factor to be a set of smallest integer. Very similar as we used to do for the crystallographic direction. We said that once we find the indices for the crystallographic direction, we have to multiply by a number, and this, all the indices should be multiplied by the same number to end up with the smallest set of integers that form this crystallographic direction. So here you're gonna do almost the same thing, but to do it basically, because we could either multiply or divide the obtained intercept by a common factor to be a set of smallest integer. But before this step, there is another step that we have to apply the reciprocal over this intercept. What is the reciprocal? To get rid of this infinity, because the infinity, it is infinity, so we have to get rid of it. To get rid of it, it means that you're gonna apply the reciprocals of all of these values. And this is another step that should be squeezed between the first two steps and the third step. It makes sense. But this reciprocal step, it is not essential to be done all the time. It depends actually on the, and in this special case, especially in all the cases, since we are investigating the plane in one single unit cell, in many of the cases, in most of the cases, you could say that over 90% of the cases, we have to apply this step of the reciprocals. The reciprocal, it means that you're gonna, like for example, the 1/2, which are the intercepts. So we got the intercept with the x as infinity, the intercept with the y as -1, and the intercept with the z as half, because we're gonna get rid of this a, b, and c. So these are the intercepts. Now you're gonna flip. Flip, it means that you're just gonna find the reciprocal of all of these numbers. So the reciprocal of the infinity, it is 1/infinity. The reciprocal of any number, it is 1 over that number. You're just gonna put it in the denominator and 1 on the top. So the 1/infinity gives 0 from mathematics. 1/infinity gives 0. So the reciprocal of the infinity, it is 0. What is the reciprocal of -1? So the -1, it will be 1/1. You still have -1. What is the reciprocal of 1/2? So it will be 1/1/2. So the 2 will be moved to the top, so it will be 2. So this step, you're going to apply it in many of the cases. You could say for all the cases, an example that we're going to consider, we're going to apply this reciprocal. But there are some other cases that this reciprocal step, it is not essentially to be done. So that's why we didn't include it in the general procedure. But in this general procedure, in one of the essential steps that you have to apply, and it should be squeezed here between step 1 and 2 and 3, you're just going to apply the reciprocal. Because in many of the cases, you're going to end up with fractions. Some of these indices will be fraction. It means that you are going to apply the reciprocal. Make sense? So once you apply this reciprocals, you're going to end up, as we mentioned, 0, -1, and 2, right? So these are the reciprocal step. Then your objective is just to do reduction, to apply this step number 3. Multiply or divide all the indices by a common number, a common factor. All of them should be multiplied by the same number or divided by the same number, with the objective of making them the smallest set of integers. All of them integers, and the smallest set of integers. This is the condition. But for this case, it is this reduction step. This should be related to step number 3. So this step number 3, it is not necessary. It is unnecessary in that case, in this example. Why? Because all of them, the 0, -1, and 2, all of them, these are the smallest set of integers. All of them are integers. And one of them is 1. 1, there is no smaller than 1 in terms of integer values, right? It means that there is no reduction that can be done over these 3 indices. So the last step, which is step 4, is just to enclose all the 3 indices that we got in parentheses, circular brackets, as already given here. Don't use square bracket. If you're going to use square bracket, this is going to indicate the direction, which means that here we are talking about a plane. The plane, it should be squeezed or enclosed in parentheses, as already given here. This gives the crystallographic plane for that plane, or the Miller indices for this plane. Make sense? So let us consider another example here. But in this example, we are required to draw. So in that example, we explain the steps. So this is the procedure, how you can find it, how you can identify the 3 Miller indices for a given plane. That this plane was given to us and we were interested in finding the 3 indices. But how about if the 3 indices were given and you are required to draw this plane? So how you draw this plane, it could be tricky to some of you, but you can reverse the procedure. Work the opposite way. Like for example, these are the 3 indices. So we do have the x and y and z. So the indices were given in this form. So these are the indices. We do have the 0 with the x, -1 with the y, and 1. We agreed that if you're gonna put par on the top of the number, this indicates the negative sign. So this indicates that you do have -1 for index for the y direction. Make sense? So then what you're gonna do, you're just gonna apply the reciprocal for all of these numbers. So it means that you're just gonna divide 1/0. This is gonna give us infinity. 1/0 gives infinity, and then you're gonna have 1/-1, and 1 over 1. It means that we just doing the same procedure, but instead of moving from the intercepts, going down to the enclosure, to the indices, no, we are going up. We start from the indices, then we are doing the reciprocal, then we're gonna identify the intercept. So this means that here we're gonna have the intercepts. So this indicates that the x-axis will be intersecting with the plane at infinity. So the intercept of the plane with the x-axis will be infinity. Why? Because we applied the reciprocal, which is 1 over 0. Then the y-axis will be intersecting with the plane at the -1, because 1 over -1 is just -1. And the z will be intersecting with the plane in the 1 point at 1. So this means that this is infinity A, and this should be -b, and this should be 1c. Agree? Then you're gonna go to the given unit cell. You're just gonna draw or construct the unit cell. And assume any 0 point, assume any origin point. As usual, we're assuming at the lower back corner of this unit cell, which as given here. So you're gonna draw this unit cell, then over this unit cell, you're gonna specify the intersection, the intercepts, with the axes that do physically intersect with the plane. Remember that the x-axis, it is parallel to the plane. Why parallel? Because it has infinity intercept. But the y and the z both are intersecting with the plane. At y intersect with the plane at -b. So it means that this is the y-axis, this is the positive direction. So you're gonna move in the negative direction at distance equal to b, and then you're just gonna mark a point. So this is gonna give you the intercept with the y-axis, which is -b. Then how about the intercept with the z-axis? You're gonna do the same. With the z-axis, it will be 1c, which should be on the top here, because this height, this is the z-axis. 1c it is positive. It means that you're gonna move in the positive direction and move vertical from the 0 point c distance, 1c, which gives you this point. So this point is the intercept, or the point of intersection of the plane with the z-axis, and this point is the point of intersection of the plane with the y-axis. If you connect these 2 points, definitely they should give you an edge within this plane. This is one edge in the plane. How about the x-axis? Is there any intercept with the x-axis? No, it is in infinity. This indicates that the plane should be parallel to the x-axis. Parallel to the x-axis, it means that from the 2 points that you specified, you're gonna draw 2 lines. From each point, you're gonna draw a line that is completely parallel to the x-axis. So again, I have specified 2 points over y and z. Why y and z? Because they do intersect. They do have intercepts with the plane, -1 and 1. I've identified these 2 points. Then you're gonna connect them together. This is gonna give you an edge, one edge of the plane. Then in the meanwhile, you have this plane that it should be parallel to the x-axis. Why? The intercept is infinity. There is no intersection. So from this point, you're gonna draw a line that is completely parallel to the x-axis. This line will be parallel to the x-axis. And from the other point, you're gonna draw another line that is also parallel to the x-axis. This gives other 2 edges. Any plane, it could have like a rectangular form. It would be triangle. It would be anything. It depends. This one, since it is parallel to one of the axes, definitely it will be rectangular in the shape. So this is gonna give you one edge by connecting these 2 points, and this is the second edge that should be parallel to the x, and this the other edge that should be parallel to x. Why parallel? Because there is no intercept. Then you're just gonna end up with a point here, another point there, connect them together, you're gonna end up with the plane. So this is the plane with these similar indices 0, -1, 0. 0, -1, 1. Make sense? So this is simply how we can apply this procedure. You're gonna start from 0 going to 4, or 4 going to 1, in case that you are interested in drawing the plane or identifying the indices for a given plane. So you have to practice the 2 approaches. For a plane that is given, what should be the indices? For indices that given, draw the plane. Make sense? So let us consider these examples for more demonstration about the thing that we explain. Assume that this is a cubic crystal. Remember that we're still working on identifying the plane for all crystal systems except the hexagonal. The hexagonal, it has another approach because it should be represented as 4 indices not instead of 3. So it is required for this plane, for example, which is highlighted by blue, that is located in a cubic unit cell, as this is the x, y, z axes as already given. And it is required to identify the Miller 3 indices for this plane. Apply the procedure. So step 0, is it applicable or not? No, it isn't. Why? Because the 0 point, it should be in the back, and this plane, it is kind of slicing this cubic crystal into 2 pieces. One piece and the other piece. It is exactly in the middle. This is like a knife, something like something slicing the unit cell in the middle. So there is no intersection of this plane with the origin point, with the 0 point. The origin point should be on the back, here. Make sense? So this is the O point. It is not intersecting with the plane. It means that we're going to skip step 0. Then what? Step 1 is just to identify the axes who are intersecting, physically intersecting with the plane. It is clearly seen that the plane do intersect with the x-axis at this point. Agree? This is the x-axis and it intersects with the x-axis at this point. And meanwhile, it do intersect with the y-axis at this point. So this is step 1. What is the intercept? Then your objective is just to write x and y and z to specify the intercepts. So the intercept of the plane with the x-axis, it do intercept at positive 1a. So it is positive 1a. Agree? And also do intercept, or the intercept of the plane with the y-axis. It is positive 1b, because this distance should be 1b. So also it is 1b. Make sense? So this is for step 1. But in step 2, you're just gonna seek or find any plane or any axis, any axis that is parallel to the plane. This plane, it has no intersection to the z-axis. The plane, it is located like this way, and the z-axis, it is somehow in the back, right? So both they are parallel. The plane, it is parallel to the z-axis. If you try to extend the plane and up and down, and the z-axis up and down, they will not be intersecting at all. It means that they are parallel together. So this means that the intercept of the plane with the z-axis, it is infinity. So this is step 1 and 2. It means that just to find the intercept. Then you're just gonna apply the reciprocal. Reciprocal, it means that you're just gonna have 1 over 1, 1 over 1, and 1 over infinity. 1 over 1 gives 1, and 1 and 0. 1 over infinity gives 0. Make sense? So this gives us 3 indices, 1, 1, 0. All of them are integer. The 0 is just integer. Okay? So all of them are integer values, and all of them are ones. It means that there is 1 and 1. There is no more than 1. And the one, this is the smallest integer value, right? This is the smallest integer number. It means that there is no reduction that can be done over this step. So we are in a good shape. That's fine. So we're just going to carry on the indices as they are. So we're going to have 1, 1, and 0. Then the Miller indices, your objective is just to represent them in parentheses, 1, 1, 0. This gives you the Miller indices for this crystallographic plane. Make sense? Let us repeat the same procedure over this red highlighted plane. Step 0, it is not applicable. Why? Because the origin, it is on the back. The origin, it is on the back, and this plane is not intersecting with the origin. So it means that we are going to skip step 0. Then what? You're just going to move directly to step 1. In step 1, you just identify the axes who are intersecting with the plane. This plane, it do intersect only with x-axis at this point, right? It do intersect with x-axis at this point, which is half of a. But it is parallel to y and parallel to z. This plane, it is looks like this way, and this is the y-axis. So they are both parallel, and the z-axis also standing. So both are parallel. So the x, the y, and z, they are parallel axes to this plane. So it means that in step 1, the only axis that do intersect with the plane is x-axis, and the intersection point is located at a over 2. So this means that the intercept with the x-axis, because there should be x, y, and z. So the intercept with the x-axis, it is half of a, and the intercept with the y-axis and z-axis are infinities according to step 2. We said that if the plane is parallel to any axis, both the intercept as infinity. So we're gonna have infinity and infinity. Then you're just gonna apply the reciprocal, which is 1 over half gives 2, and 1 over infinity gives 0, 1 over infinity gives 0. Then what? So in this step you have to do reduction. Why? Because all our integers, forget about the zeros, we have only one integer, which is 2. Is this 2 the smallest integer value? No. It means that you have to divide all the indices by 2. So if you divide 2 by 2, so you're just going to do reduction. Divide by 2, divide by 2, divide by 2. This is going to give you 1 and 0, 0. So the Miller indices, they should be 1, 0, 0. They shouldn't be 2, 0, 0. It is wrong. This is because this is a standard approach. This is a standard methods of how we are defining or representing the crystallographic planes in crystal systems. So we have to stick to it. It means that we have to do the reduction. 2, 0, 0, it is not a crystallographic plane for this case. There is no crystallographic plane with 2, 0, 0. It is totally doesn't make sense. Okay, so it should be 1, 0, 0. Why 1? Because we are seeking the smallest integer values. 0, 0, there is no big deal with the zeros. The challenge or the deal with the 2. 2, it is not the smallest integer. Divide by 2, all. So you're going to end up with 1, 0, 0. Make sense? So let us consider this example of this plane that is red highlighted and represented in this cubic crystal. So this is also another simple example. If we try to apply the step 0, it will not be applicable. Why? Because the 0 point, it is, or the origin point, it is not intersecting, or the plane, it is not passing over this origin point. So it means that the step 0 will be skipped. Now we're gonna move to step 1. In step 1, you just define the axes who are intersecting, physically intersecting with the plane. So this plane, it do intersect with the x-axis, y-axis and z-axis as shown in the figure. It is clearly seen that it do intersect with the x-axis at this point. This point, it is half of a, and it intersect with the y-axis at this point, which is 1b, and in the meanwhile it do intersect with the c point with the z-axis as 3 over 4c. This 3 over 4 half a and 1b, this data will be provided. It means that it will be specified over the graph that it is 3 over 4c. And also it will be defined here as a over 2. Make sense? So anyway, this plane, it do physically intersect with the x, y, and z axes in 3 points, and we have identified these intercepts. So this is for step 1. So the intercept with the x-axis, it is half. With the y-axis, it is 1. With the c-axis, it is 3 over 4, and all are positive. Why? Because the plane do intersect at the positive directions. Make sense? How about step 2? Step 2, you just gonna identify any axis that is parallel to the plane. This plane, it is not parallel to any axis. There is no axis who are parallel, which are parallel to the plane. It means that we are going to skip step 2. Then we're going to move to the reciprocal. We're going to apply the reciprocal. It is half. So it will be 1 over half gives 2, right? 1 over half gives 2. 1 over 1 gives 1. And 1 over 3 over 4 gives 4 over 3. After the reciprocal, we end up with 2 indices are integer, while this one is fraction. So we have to get rid of the fraction. How? Multiply times the smallest denominator. The smallest denominator will have only one denominator, which is the 3. So I'm going to multiply all the indices times 3. If you multiply times 3, this gives us 3 times 2 gives 6. And 3 times 1 gives 3. And 3 times 4 over 3 gives 4. So this, now we end up with 3 integers. So in the beginning, we had no integers. We had only 2 integers and 1 fraction. So we have to get rid of the fraction. Then we end up with 3 integers. Then you have to investigate whatever all of these three integers are the smallest combination of integers or not. The smallest integer number, it is 1. But the smallest one of this integer is the 3. So the question is the 3 or the 6, it is divisible by the 3, can be divided by the 3, or the 4 can be divided by the 3 to give you integer value? No. It means that this smallest integer, which is 3, it will be the smallest. It means that these three indices will be the smallest integer combination. So once you end up with all R integers, you're just gonna try. If none of them is 1, because the smallest integer value is 1, so there is no more reduction than the 1. But here we don't have 1s, we don't have 3. This 3, this is the smallest integer. Then you're just gonna try to divide 6 over 3. 6 over 3 gives 2. But 4 over 3 will not give us an integer value. So it means that this combination will be the smallest combination of integers. It means that the Miller indices will be 6, 3, and 4. You got my point? So your objective, actually, when you do the reduction step, is just to try to get rid of all the fractions. Once you're gonna end up with a set of integers, you're gonna choose the smallest integer. If it is 1, you are okay, directly these are the Miller indices. If it is not, if this integer is not 1, like 3 or any other number, try to divide all the other indices by this number. If any one of the indices gives you a fraction, so it means that there is no further reduction that can be done. But of all, after the division, after you divide all the other indices by this smallest number, like the 3, in this case we got the 3, this is the smallest integer. So you're just gonna try to divide 6 over 3 gives 2, integer. 4 over 3 gives fraction. Okay, so there is no further reduction over the 6, 3, 4. But if you divide 6 over, for example, if we do have a combination, if we got the integers as 6, 3, and 12 for some reason. So the smallest integer is 3, so you're gonna divide by 3. This is gonna give us 2. And you're gonna divide by 3, this is gonna give us 1. And you're gonna divide by 3, this is gonna give us 4. So this is the Miller, these are the Miller indices. Why? Because you got 1. The 1 is there. This is the smallest integer, so there is no more reduction. But if one of the smallest integer, it is not 1, you should try to divide by this number all the indices. If you got integers, so this will give you the smallest, this is going to give you the Miller indices, or the smallest combination of integers. But if you try to divide by that number, and for some reason one of the indices it is a fraction, all right, so there is no further reduction, and in that case the last combination of integer that you got, this will be the Miller indices. Make sense? Now let us consider this example. Over this previous example, none of the planes was intersecting with the origin point, right? How about if you do have a plane that it do intersect? It means that we have to apply step 0. Like for example, plane A, which is this one, this plane. I'm just gonna mark this plane A, which have this triangular shape. All right. So this is the origin point. As clearly seen that this plane do intersect with the 3 axes at the origin point, at the 0 point. So it means that we have to apply step 0. Why to apply step 0? Because in this case, we will not be able to identify the intercepts of this plane with the x, y, and z axes. It do go over the 0 point. It means that all the intercepts will be 0, so you're going to end up with infinities as indices, which doesn't make sense. Make sense? So it means that we have to move. We have to apply one of the 3 approaches. Either to draw another plane that is parallel to the original plane, which I believe will be complicated for many of you to do so. Unless your drawing and imagination it is kind of good, so you can do it. The other option is just to draw another unit cell that is parallel to the original unit cell or next to it. And in that case, you are going to investigate the intercepts of this plane with the new axes of the new unit cell. Or the simplest approach that I told you about it, just move the 0 point, move the origin point to any other corner. So, and this is what I'm going to do. So simply, if we try to move, just let us, for example, you can move this 0 point to this corner, for example, and then you're gonna investigate the intercepts, or you can move it here. But while you try to choose the movement, the new location of the 0 point, be smart. Be smart to choose the 0 point, new location, that gives you the intercepts in an easy way. That gives you this plane clearly intersects with the new locations of the new axes. Because once you move the 0 point, some of the axes will be moved as well. Like in this case, for example, in this example, the best way to move the 0 point is to move it to this corner. Why? It will be clear. It will be much more easy to investigate the intercepts if you move to that corner. So for example, to move the origin to this corner, it means that in the meanwhile, you should move the x-axis up and the y-axis will be moved up as well, right? Because you should have the plane or the coordinate system, it should be z, x, y, z. All are intersecting at the same point, the origin point, which is the 0 point. Make sense? Now, your objective, as clearly seen, the plane A, I'm working over plane A, forget about plane B. Plane A is not intersecting with the origin point, so we have done of step 0. Now let us apply the other steps. The first step is just to identify the axes who are intersecting with the plane. We do have the x-axis, it do intersect with the plane at this point, which is half as already given here, right? It means that it do intersect with the x-axis at half A. And the y-axis, it do intersect with the plane A. We are working over plane A. This one. Don't be confused with the plane B. Forget about B. Just focus over this triangle. So the plane, it do intersect with the y at 1B. The question is, does the plane intersect with the z-axis? Yes, it do. It do intersect with the z-axis because you should consider that z-axis is extended all the way up to positive infinity and all the way down up to the negative infinity. So the extension of the z-axis down, it will meet the plane at this point, which was the previous, the original 0 point or origin point. This point will be negative 1c according to the new 0 point or origin point. We have moved the origin point on the top. It means that the intercepts of the z-axis with the plane, they're gonna intersect together at negative 1c down. So this gives us the intercept. So your objective is simply just to have the intercept, specify the intercept of x, y, z. So the intercepts with the x, it will be at half A. With the y will be 1b, and both are positive, but this will be negative 1c. It means that the intercepts will be half, will be 1, will be negative 1. Then you just gonna apply the reciprocals to these numbers. So the 1 over 2, 1 over 1 over 2 gives 2. The reciprocal of this number, the reciprocal of this one is 1. The reciprocal here, it is negative 1. Make sense? Then you're just gonna work over the reduction. You're gonna try to reduce the number to the smallest integers. There is no reduction is needed here. Why? Because the smallest integer number is there, which is 1. So there is no further reduction that can be done. It means that the Miller indices for this crystallographic plane will be 2, 1, negative 1. We agreed that the negative should be put as a dash on the top of this number. Make sense? So this gives us the Miller indices for the crystallographic plane A. So this is simply how we can identify the 3 Miller indices for a crystallographic plane that belongs to all the crystal systems except the hexagonal crystal structure. The hexagonal is a special one. Make sense? Now let us move to another point here, which is very similar to the thing that we discussed with the crystallographic directions. We said that in crystallographic directions, you may have some directions who are equivalent. And we have specified the conditions that you should have 2 directions or more, they are equivalent. The same thing here for the crystallographic planes. The crystallographic planes, they could be equivalent under the condition. What is the condition? That any 2 planes who are parallel within the same unit system or the same unit cell, they are 2 equivalent planes. And by definition, they should have identical indices. So again, there are 2 things here. all the equivalent crystallographic planes, first they should be parallel. So any plane that is parallel, it is equivalent to the original one. So it means that this plane, this blue plane, and this one, all of them are parallel. All of them are equivalent. These green planes are equivalent. Why? Because they are parallel to the original plane. These yellow planes all of them are equivalent. Why? They are parallel. So any plane, any two planes or more who are parallel, they are equivalent planes. And their Miller indices, they should be identical, the same identical indices. It means that what is the index? What is the Miller indices for this plane? This is 001. How about this one? It is also 001. This one 001. So they should have the same Miller indices. This is not the case for the crystallographic directions. You may have two crystallographic directions with different indices, but they do equivalent. If the spacing between the atoms is the same. They do have different indices, yes, but they do equivalent if the spacing between the atoms is the same. This is for the crystallographic direction that we discussed last meeting. But the good thing of the plane that there are two things. They should be parallel, and if they are parallel, they're gonna be equivalent with the same indices. The same thing, the indices for this plane is 110 and the others also 110. The same thing, this here it is 111. The indices for the other planes will be the same 111. Make sense? So that's why this explains why in step 0 we can draw another plane that is parallel, because it does, even moving the origin to another point, it will not change. You're gonna end up with the same indices, because moving the origin or drawing another unit cell or drawing a plane that is parallel to the original plane, you're gonna end up with the same Miller indices. It means that you're gonna deal with equivalent planes. So we are interested in the Miller indices of this plane. So it is not necessary to work over this one. You can work over any other plane that is parallel to it, that is equivalent to it. You're gonna end up with the same Miller indices. Why? Because we mentioned, as already given here, all equivalent crystallographic plane, they should be parallel, and in the meanwhile, they're gonna have identical indices. Make sense? So this is for all the crystal systems, and even these equivalent things are applicable to the hexagonal crystal structure. But for the hexagonal crystal structure, there is a kind of a challenge, there is difficulty, there is a problem with the hexagonal crystal structure. So now I'm going to explain and show you how we can identify the Miller indices or the indices for a crystallographic plane in a hexagonal crystal. Okay, so for the hexagonal unit cell, as we mentioned, there is a problem of identifying the equivalent crystallographic planes for a hexagonal crystal structure if we decided to use the 3-index Miller notation, as we did for the other crystal systems. So that's why typically the same as we did with the crystallographic direction, we have to use the Miller-Brevis system that include 4 axes instead of 3 axes, which are A1, A2, A3 in addition to the Z. So for crystals with hexagonal unit cells, it is desirable that all equivalent planes, they should have the same indices. And this cannot be happen unless we are using the Miller-Brevis system, the 3 axis system. It will give the equivalent planes with different indices. So this is accomplished by the Miller-Brevis system shown in the figure. As I mentioned, A1, A2, A3, and Z. We are replacing the 3-index XYZ with the A1, 2, and 3, and Z. For hexagonal unit cells, the crystallographic plane is represented using 4 indices. These indices are H, K, L, and there is I between K and L. So the HKL very similar to the other 3 indices in many of the cases, but there is a special index, 4th one, that it will be squeezed between K and L. That's why we have HKIL, and all they should be enclosed in circular bracket or parentheses as we discussed for the crystallographic planes. The HKL indices are determined by the intercepts of the axes A1, A2, Z respectively, like the H. This is the intercept with the A1. K, it is related to the intercept with the A2. And L, it is the intercept that is related to the z-axis. So these are three axes. You're gonna find the intercept the same way that we explained for the other crystal systems. But the I, by the way, it is the intercept of the plane with the A3 axis. So the I, this is the intercept of the plane, the crystallographic plane with the A3 axis. If you couldn't able to identify the intercept of the plane with the A3 axis, you can directly calculate the I index from this relation. I index all the time, it is I equals negative h plus k. What is h? This is the intercept with A1, k is the intercept with A2. So the negative of their sum, this is gonna give us the I index, which should be the intercept with A3. So it means that if you can identify the intercept with of the plane with A3, that is fine. This is gonna give you I, or the other option you can directly calculate. You should end up with the same value. Make sense? So let us consider this example of this crystallographic plane, and let us apply the same procedure. The same steps that we explained before for the other crystal system is still applied. But the new thing, instead of using and intersecting with the conventional x, y, z, we are going to find the intercepts with A1, A2, A3, and z, and we're gonna use the 4 indices. But still, the step 0, step 1, 2, and 3, and 4 that we explained before will be applicable. We still gonna apply them. So, step 0, if this plane do intersect with the 0 point, remember that the 0 point for this hexagonal crystal at this center, this is the origin point, this is the 0 point. Does this plane do intersect with this point? No. This plane is going down, it is not intersecting with this plane, with this point O. So it means that we are going to skip step 0. But if it do intersect, it means that we have to move the origin to another point or do any other thing. Like moving the origin, for example, up on the top or down. For this hexagonal, you're going to have one of two options. Either moving this origin to the top or just put it over the top surface or the bottom surface. Make sense? But anyway, in this case, there is no intersection with the origin. It means that we are in a good shape. Skip step 0, move to step 1. What is step 1? Your objective is just to identify the axes who are intersecting with the plane, physically intersect with the plane. We do have 4 axes, A1, A2, and A3, and Z. So, do you think that A1 do intersect with the plane? Yes, it do intersect with the plane at this point. This is A1 axis, and the plane clearly intersect with the A1 at this point. So this point, it is a point of intersection along A1, and this should equal to 1A. The intercept will be 1A. If you remember from the drawing that we represented the last video, that this hexagonal base, these are the geometry that you should consider. That this is the center point, this is the origin point. This distance should be A, this is A, this is A, this is A. All of these distances are equal to A. In addition to these side edges all are A's. They are equal. So these are the specifications that you should know and understand about this hexagonal base. So it means that this distance from O, the origin point or point C to point A, which is this distance is already A, it means that the intercept of the plane with A1, it do intersect with the A1 at 1A. How about A2 axis? A2 axis, which is this one. Do you think that this plane, it do intersect with A axis? Yes, it do. How? It will intersect in the back. Remember that this is an axis that will be extended all the way till the positive infinity and all the way down till the negative infinity. If you remember the last meeting, we explained that over this projection of the base, you can represent this should be the A1 direction and this should be the A2 direction, that you just gonna skip one vertex or one corner, then you're gonna draw, this gonna give you the A2. This plane is represented the edge, this edge in the plane, this edge. It will be coincident over this edge, right? This is the edge of the plane. Agree? This is A1, which gives us this point, which should be this point. This edge, which is this edge. So this edge is a part of the plane, and if you try to extend the A2 down in the negative, they're gonna intersect at a point. This point will be located at the negative 1A, at the negative 1 with respect to the A2. It means that the intercept or A2 will intersect with the plane at a point which is this point is located in the negative side at a distance A of A2. It means that this will be negative 1A with respect to A2. What is the intercept with A3? If you are interested in finding the intercepts with respect to A3, you can do it. Let us try to do it for the A3. A3, what is the intercept of this plane with the A3? It could be a little bit challenging to some of you to figure out what is the intercept. So that's why don't bother yourself by calculating or finding the intercept with the A3. But anyway, you can calculate it directly. But as you can see, for this plane, it is not intersecting with the A3. It is parallel to the A3. How it works this way. Like you do have the plane, and A3 is gonna go this way. So both are parallel. A3 and the plane, they are parallel. There is no intercepts between A3 and the plane. And I'm gonna prove this to you. For now, it is infinity. If whatever you understand, it is parallel or not, there is no big deal with the A3. If you can figure out the intercept with the A3, that is fine. If not, you can calculate its index, which is I at the negative of h plus k. Very simple. So let us skip the talk about A3 and let us move to the Z axis. What is the intercept of this plane with the Z axis? So this is the Z axis. So this is the plane. It's going to intersect with the Z axis at point G. As you can see, if you can observe it, going starting from this edge down here, and it goes up till it do intersect with the vertical axis, which is standing. The intersect point will be at this point G. This point is located at a distance C in the positive Z direction from the 0 point, right? So this vertical distance from the origin point or 0 point up to the G point, it is C in the positive positive direction of Z. It means that this is 1C. This is the intercept. So we got the intercepts with the 3 axes. So we got these intercepts. So these are the intercepts. Just let us apply the previous steps. So next step is just to apply the reciprocal. Find the reciprocal. So the reciprocal of 1 is just 1. Of negative 1, it is negative 1. And of the infinity, because there should be infinity here for A3, so it will be 1 over infinity. This is going to give you 0, the reciprocal of the infinity, and the reciprocal of 1 is just 1. So you're going to end up with set of integers, right? You're just going to end up with set of integers. And the minimum integer value, it is 1. It means that we are in a good shape. So these are the Miller indices. So these are the indices that we are seeking for this crystallographic plane. It will be 1, negative 1, 0, and 1. Make sense? So how about what should be this index? Just to prove to you that this index, it should be I, right? This index is I. We said that according to this expression that I equal to the negative h plus k. What is h? This is h. This index is h, and this is the k. So the I, it should equal to the negative of h plus k. So equals the negative of h, which is 1, negative 1, which is k, is negative 1. This is going to give us 0, and this is indicate that this expression is correct. So that's why don't bother yourself with finding the intercept with the A3. That's okay if you find the intercept with the A1 and A2 and Z. Then automatically you can calculate I using this expression as negative h plus k. You're going to end up with the same result like if you try to figure out the intercept with the A3. Make sense? So this is simply nothing new in comparison to the previous system, but the new thing is this extra index. And instead of dealing with X, Y, Z, you're going to deal with A1, A2, A3, and Z axes, 4 axes. Make sense? Let us consider this example as well. This is a crystallographic plane that is represented over this hexagonal crystal, and we are interested in finding the indices of this plane. So first, you're going to try to find the intercepts with the 4 axes, A1, A2, A3, and C. Make sense? So what is the intercept of this plane with A1? Do you think that it do intercept with A1? Yes, it intersects with the A1 at this point. This point, it is 1A. So it means that the intercept with A1, it is 1. But in the meanwhile, it is parallel to A2. Parallel to A2, why? Because there is an edge. Do you see this edge? it is parallel to A2. Any edge that is parallel, if it is parallel to an axis, this gives an indication that this plane will be parallel to this axis. So this edge here is parallel to the A2 axis. It means that A2 has no intersection with the plane. It means that the intercept of the plane with the A2 it is at infinity. How about A3? Don't bother yourself by investigating the intercept with the A3. But if you are interested, this plane will intersect with the A3 axis at this point. If you extend the A3 in the negative direction, it will intersect with the plane at this point. This point will be negative 1a. So that's why it is negative 1, the intercept with A3. But as I mentioned, don't bother yourself by the A3. You can skip this term, this row, or this column and directly move to the C. See, this is the intercept or Z. The intercept with the Z axis, how much it is. This plane, it is extended and is going to intersect with the Z axis at this point, at the C. This point is located from the level down. This is the 0 point. This vertical distance from the 0 to this point on the top, it is C, which equivalent to the height of this hexagonal crystal. It means that it is 1c and it is in the positive side. So that's why it is 1c. So we got the intercepts as 1, infinity, negative 1 and 1. Then you're going to work over the reciprocals. The reciprocal of 1, it is 1. Of 1 over infinity gives 0. And the negative 1 gives negative 1, 1 gives 1. Then you're going to work over the reduction. So these 4 indices, there is no reduction for them. So you're going to end up with the Miller-Brevets indices directly as 1, 0, negative 1, 1. Make sense? How about I? If you didn't find if you couldn't able to identify the intercept with the A3, I we mentioned it is negative of h plus k. H here it is 1, which is this index, and k it is the 0. So this is gonna give us negative 1 plus 0, which gives us negative 1, and this is clearly seen. It is negative 1 for the I. Make sense? So this is simply how we can identify the crystallographic plane for a hexagonal crystal and any other crystal system. Make sense? What is the importance of these crystallographic directions, crystallographic points, crystallographic planes that we were discussing? There are lots of important things, so many things that we gonna use these definitions of the crystallographic plane, especially if we are interested in investigating the atomic structure of any crystal. We said that all the properties of the material related to the material structure. And this is the main concern and objective of this course, is just to understand how the material properties are related to its structure, like the atomic structure. So that's why over chapter 2 and 3, we are focusing somehow, the focus is over the atomic structure, especially in chapter 3. We are focused on the atomic structure of crystalline material or crystalline solid material, this crystal, this unit cell, FCC, BCC, HCB, and so on. So, for example, some of the properties could be related somehow, and this is going to be much more clear, especially in the next chapters. Some of the properties are related to some specific crystallographic planes within the material, or within the crystal structure. Like if you do have an aluminum, which is made of FCC crystals, there are some specific properties, some specific things that are usually happening to the atomic structure over a specific plane. So it is important to know how you can identify the crystallographic plane within a unit cell. Like for example, one of the important planes in any FCC crystal or even BCC crystal structure is the 110 plane. There are lots of things that happening over this plane. One of the things, for example, is the dislocation. If this unit cell will be scattered, will be broken, will be cut, it is likely to be happen over this plane. This will be explained in the next chapters. So that's why it is important over chapter 3 to know how you can define the crystallographic planes. Because in the chapter 4 or 5 or the next chapter, once we mention plane 110, you should understand the plane, its location in the crystal or the unit should come into your mind directly. I will not draw, this plane will not be drawn anymore. Once we mention, for example, 111 plane, you should understand how it's gonna look like inside the unit cell directly. So that's why it is important in this part to understand how we can identify and define a plane within a specific unit cell. Like, for example, as I mentioned, one of the important planes, for example, is the 110 plane in the Fcc or BCC crystal structure. So this plane, it will include some atoms, and these atoms will be somehow arranged over this plane. One of the other benefits of this crystallographic direction things, as we discussed in the start of the class, if we decided to look to the material microstructure and we're gonna use a microscope with a very high resolution and zooming and magnification factor, that we can see the atomic arrangement. So the atom could be arranged in this way, or it could be arranged in this way, or in other method. So from the arrangement of atoms, we can identify the type of the crystal. Is it FCC, BCC, or any other crystal structure? This is from the image that we're gonna get from the TM. This is the image that can be identified from the image that we're gonna get from the microscope. Once we see and get a shot of the atomic structure that shows the arrangement of the atoms over a specific plane, we can identify the type of this crystal. Is it FCC or BCC? So the question is, what is the atomic arrangement of a plane, of the plane 110? Why this is a plane? Because the indices are confined or enclosed in a circular bracket, in parentheses. For FCC or BCC, what will be the shape? What will be the arrangement? How these atoms will look like if we decided to look at it through the microscope over a plane which is 110? What will be the arrangement of these atoms? So, as we discussed before over the part 1 of the chapter, the Fcc crystal structure should have atoms that located at the corners. There should be one atom at every corner. In the meanwhile, there should be an atom that is located at the center of every face. This is for the Fcc crystal structure. Just focus over the Fcc crystal structure. So now let us identify the plane 110. 110, if we decided to apply the procedure that we explained, we should start from the indices. Then we're gonna find the reciprocal. Then we are going to find the intersects. So for example, if the indices are 1, 1, 0, this is X, Y, Z plane axes. This is cubic crystal, so it is not hexagonal, so 3 indices. That's why we already given the plane at 3 indices. So these are the indices. The reciprocals will be 1, 1, and infinity, because 1 over 1 gives 1, 1 over 1 gives 1, 1 over 0 gives infinity. This means that the plane, it will intersect. So these are the intercepts. The intercepts will be 1A and 1B and infinity C. So it means that it's going to intercept with the x-axis at 1, with the y-axis at B, and with the z-axis it will be parallel to the z-axis. So if you decided to draw, let us draw. This is like the second example that we solved today for the drawing the plane for a given indices. So if we assume that this is the 0 point, and this definitely is going to be the x-axis, this is going to be the z-axis, and this is going to be the y-axis. So the intercept or the intersection of the plane with the x-axis will be intersect at 1A. So this is the first intersect point. And it will intersect with the y-axis at 1B. So this is the second intercept point. Then you're just going to connect these 2 points together. This is going to give you one edge of the plane. In the meanwhile, it is parallel to Z. Parallel to Z, it means that from that point, you're just going to draw a line that is parallel to Z. And from the other point, you're going to draw another line that is parallel to Z. This is going to give you the 3 edges. Then you're just going to close the shape to end up with a rectangular plane. So this red thing, this is the plane 110. So the question is, what are the atoms that are intersecting or located over this plane? According to the Fcc crystal structure, we should have an atom that is located at every corner. It means that this atom, it belongs this atom C, which it should be this atom, it belongs to this plane. Its center is located over this plane, at this corner. This atom B is located at the center of the top face, and this edge is located over this top face. It means that this point B, it is over this edge in the middle. It is one of the points that located over this plane. So that's why you're gonna find atom B. Also, you're gonna find another atom, which is atom A, that located at the other corner. If you're gonna go over this edge, there is no other atoms. But at the end, there is another atom, which is atom D. The same thing over this edge, there is atom E, which is located at the center of the bottom surface. This is one of the atoms located within this plane over that edge. And if you move till the end of the edge, you're gonna find the atom F, which is located at the other side. If you're gonna go up, there is no in-between atom. There is no atoms in the middle, except C and F. And also you have to investigate the core over the plane, over this plane, this red highlighted plane. Do you think that there is any atom in the middle over this face? No, all atoms are distributed over the edges of this plane. Why? Because this is Fcc crystal structure. So for the Fcc crystal structure, the arrangement of the atoms over this plane will be arranged in this way. Like you're gonna have one atom at this corner, one atom at the other corner, one atom at this corner, at this corner. So at the four corners, any plane is rectangular, so it has four corners. This plane is rectangular, has four corners. So at every corner there is an atom, and in the middle of this edge and this edge there is other atoms. But there is no atoms in the middle of that edge or this edge. Make sense? This is for the Fcc crystal. How about if we have the same plane in a cubic crystal, but this cubic crystal, it is BCC. In the BCC crystal structure, so it means that we're still gonna deal with the same crystallographic plane. We still have the same plane. It means that nothing will be different. In terms of the identification of the plane, we still have the same plane. We'll have this vertical edge and this edge and this vertical edge. So this is the crystallographic plane. What are the atoms that located over this plane? So let us do the same. For BCC crystal structure, there should be an atom at every corner. So it means that there should be an atom here. This is B dash, one of the atoms, which B dash. And if you're gonna go all the way, there is no other atoms in the middle. Why? Because there is no atom in the center of the face. But on the other side, there is another atom, which is A dash. If you're gonna go down, you're gonna find another atom, which is D dash. At this corner, go all the way, you're gonna find another atom over the other corner, E dash. But in the meanwhile, don't forget that there is an atom that is located in the core of the BCC crystal structure. For BCC crystal structure, there should be atoms at the corners. And in addition, there should be an atom that located in the middle, in the core of this unit cell. So this crystallographic plane, it is kind of cutting the unit cell into two pieces, identical pieces from the middle. So it means that this plane, it is somehow over or slicing the atom that is located in the core of the unit cell. It means that this atom C dash, which is located in the core, it belongs to this plane. It is one of the atoms that will be shown over that plane. So the arrangement of atoms over this plane will include, will be shown in this way, that at every corner there should be an atom, and in the center of this rectangular plane there should be the atom, which should be the core atom of the BCC crystal structure. Make sense? So this arrangement of the atom, it is a big deal. We are using them in doing investigation and understanding why this material has such a property. How this property or properties are related to the atomic structure. Whatever, do we have an Fcc crystal structure or BCC crystal structure, or what is the crystal structure of this material? This investigation should be done through the TM, and we should understand the arrangement of the atoms over the specific plane. We took a picture of this material at this plane, which is 110 plane. And we got either this image or this image. So based on the obtained image from the TM, we can identify the crystal structure. So that's why this crystallographic planes, it is a big deal. And it is important to understand how you can identify these crystallographic planes. Make sense? Last thing that will be mentioned here is linear and planar densities. This is the last topic of chapter 3. What are these densities? We have mentioned or discussed the theoretical density, how we can calculate it for a specific crystal structure depending on the atomic backing factor and the atomic arrangement inside and the number of atoms inside the crystal structure over the part 1 of chapter 3. But this is a different thing. The density, this gives you an idea about how dense is a direction or a crystallographic plane is filled with atoms. Like as I mentioned, there are some important planes depending on the crystal structure. Like one of the important planes is 110. So for example, if this plane for the Fcc crystal structure, is it dense or not? Is it filled with so many atoms or not in comparison to the BCC crystal structure? Which is very similar thing to the atomic backing factor. We said that this atomic backing factor gives idea how much of crowdedness of atoms are located inside this crystal structure. Is it filled, crowded atomic structure, or it is empty atomic structure? So this has a factor, this planar density. So the same thing, what is the density of the atoms over a certain crystallographic plane or a crystallographic direction? These are the linear and the planar densities. They are important. It is important to know how you can calculate them. Because why? Because there are some of the properties of the material are related to the linear density, are related to the planar density over a certain plane or crystallographic direction of this material. And this it will be much more clear when we are going to discuss especially the dislocation over the next chapters. So that's why, as I mentioned many times, the importance of chapter 3 that we are fixing methods, approaches of calculating these points, crystallographic directions and planes, because we're going to use them over the next chapters. So how we can calculate the linear density, or what is the linear density and the planar density? The linear density, it is the number of atoms that belong to a certain crystallographic direction. So again, this means that the linear density is related to the crystallographic direction. But the planar density, it is the number of atoms per unit area that are centered on a crystallographic plane. So the planar density, it is conjugate or related to the crystallographic plane. But the linear density is related to the direction, to the crystallographic direction. The linear density, it is the number of atoms. This is the equation, this is the relation, the formula of the linear density. LD stands for linear density. It equals the number of atoms which are centered on a certain direction, on a certain crystallographic direction, divided by the length of this direction. This is how we can calculate the linear density. And again, some of the properties of the material are related to the linear density, so that's why you should know how you can calculate it. We're going to use it next. So it is the number of the atoms who are centered, which are centered over this direction, divided by the length of this direction. And I'm going to give you an example how we can calculate it. But the planar density, it is very simple, it is very similar. But instead, because it is related to a plane, plane has no length, has area. Any plane, it has an area, a surface area. So that's why it is the number of atoms per unit area that are centered over a certain crystallographic plane. To explain this linear density further and planar density, let us consider this example of Fcc crystal structure. So Fcc crystal structure, what should come in mind is the shape of the structure. There should be an atom at every corner, and there should be an atom that occurs at the center of every face. And it is required to calculate the linear density of this direction. We said that any three indices is squeezed or confined in a square bracket, this indicates a direction. So here we are talking about linear density. There is no linear density for a plane. The linear density, it should be for a direction. The direction, it is 110 direction. within Fcc crystal structure. So how we can calculate it? First, you should consider an Fcc crystal structure. Second, so this is the Fcc crystal structure. This is the first step. The second step is just to identify or draw this direction. This direction, it is 1, 1, 0 direction. How we can draw a direction as we explained over the last video? You should start from the 0 point. Assume that this is the 0 point. And it is 1, 1, 0. It means that you're going to move 1A parallel to X, 1B parallel to Y. You're going to move 1A parallel to X. In the X direction, positive. In the positive X direction. Why? Because this first index is positive. Then you're going to move positive 1A, 1B. And then you're going to move 0 in the Z direction. Because this third index is 0. It means that the end point will be here. Then your objective is just to connect the start point to the end point. This is going to give you the direction. Very simple. Make sense? So the first step is just to draw the Fcc crystal structure. Distribute the atoms as we defined the Fcc crystal structure before. Then draw the vector. Draw the direction over this crystal. This is the second step. The third step, this plane, it is located, this direction, it is located over the bottom surface. So your objective is just to draw all the atoms that located over this vector, over this direction, over this line. Any atom that located over this line, draw it. So we do have this line that starts from here. We do have an atom, its center is located at the end of this vector. And there should be another atom that's located in the middle, right? And there should be another atom that's located at the end of the vector. So these are the three atoms. This is one atom. This is the second. This is the third. Three atoms who are located over this vector. Just draw them. So this is the third step. The fourth step is just to count how many atoms belong to this vector. And this is a little bit tricky. For example, this atom, or how many atoms whose centers are located or belong to this vector. For example, if we're going to consider this atom, it is not all of it, it is just half of it that belong to the vector. Because the vector comes or starts from the center of this atom, it means this half of the atom doesn't belong. This other half doesn't belong to the line, doesn't belong to this vector. Make sense? This part doesn't belong to the vector. It is not part of the vector. It is not part of the direction. Only half of the atom that is part of this vector, that is located over this vector. The same thing on the other side. The end point of the vector, it is the center of this circle. It means that this half of the circle or this atom does not belong to this line. It means that only half of the atom that is belong to this line. In addition to this entire atom, the whole atom is located over the line. It means that we're going to have one complete atom. So if I ask you how many atoms that are located over this line, we do have only 2 atoms. How 2 atoms? Half of this atom. Why? Because it starts from the center, not from the edge. And this is what conventionally happens. We start from a center of an atom. So it means that we do have only half of it. And we do have another half of the other side atom in addition to this complete atom. So we do have one whole atom, half and half. So in total, over this edge, we do have only 2 atoms. So the linear density of the Fcc crystal along the direction 1, 1, 0. So 1, 1, 0 refers to the direction, because the linear density for any other direction will be different. For example, the linear density for the 1, 1, 1 could be different. Linear density. Or it could be the same. But anyway, for any crystallographic direction, there is a specific linear density that we can calculate it based on this expression. So this expression states that you should count the number of atoms that belong to this edge divide them by the length of this edge or this direction. So what is the length of this direction? So step 1 is just to draw the crystal. Step 2, draw the vector. Draw the direction within the crystal. Step 3, draw the vector or draw the direction and allocate the atoms. Draw the atoms over this direction. Step 4, count how many atoms that physically belong to this edge. Step 5, calculate the length of the edge of the direction. What is the length of this direction? For the FCC crystal structure, this edge it should be A. This edge should be A as well. So what should be this edge? It should be the hypotenuse, the diagonal of the base. So this hypotenuse from the trigonometry of this triangle, it will be the length. So the length of the direction 110 will equal to A square root of 2 according to this triangular shape. Make sense? Some of the specification that you should understand, and this is what we have discussed before for the FCC crystal structure. Can we relate? Can we write this A, the side edge, or the crystal lattice constant A, in terms of R, which is the atomic radius? Yes. We said that for the FCC crystal structure, A equals 2 square root of 2R. This is just A times square root of 2. So if you did the multiplication, this is going to give us 4R, which also can be clearly indicated from here. If I ask you what is the length of this line, it will be 2R, because R, this is the radius of one atom. So we do have here from this point to this point, we do have 2 R's, we do have 1 R, 1 R, 4 R's. So the length of the vector, the length of the direction, it is 4R. And we do have 2 atoms. So the linear density will be 2 over R, 4R, which is going to give you 1 over 2R. This is the linear density along the direction 110 in FCC crystal structure. If the crystal structure has changed, this linear density value will be different. For example, for the same direction, 110 direction, for a BCC crystal structure, the linear density will be a different value. Make sense? This is for the linear density. How about the planar density? The same. But instead of calculating the length and dealing with an edge or a vector, we're going to deal with a plane. So what is the planar density? For the plane 110, again it is confined in parentheses. Why? It is a plane for FCC crystal structure. So over the 110 plane, as we discussed before, this plane, it will be this red plane. This edge and this edge, as we explained over the previous slides. So the step 1 is just to draw the FCC crystal structure or the crystal structure that is given to you. Step 2, identify the plane. Step 3, draw the plane and allocate the atoms that located over this plane. We just explained this over this slide. Here, we said that for the 110 plane for FCC crystal structure, this it will be the distribution of the atoms over that plane. We're going to have one atom at one corner, and we're going to have another atom and another atom and so on. So we do have one atom here, one atom here, one atom at the corner, at every corner, and one atom at the middle of these 2 edges, but there is no atoms over these 2 edges, as we explained over the previous slides. Make sense? So step 1 again is just to draw the crystal, the unit cell of this crystal, then draw the plane, then you're gonna extract the plane and identify and allocate the atoms, how they are arranged over this plane. This is step 3. Step 4 is just to count how many atoms that physically belong to this plane. Remember, the plane is this plane, what is inside, this is the plane. So what does it mean? It means that the plane, it should be the thing that is in the middle. Only, this is the plane. So how many atoms physically located or parts of atoms which are physically located inside this plane? So to identify it here, for example, is this in this atom, all of it is located inside the plane? No, only half of it. This half is the only thing that belongs to this plane. But how about the other half? It doesn't belong to the plane. Very simple. Makes sense? It is outside the plane, so we still have one half. How about the other atom on the other side? Also half of it, it is inside the plane, but the other half, it is outside the plane. So we do have half, and there is another half. So this gives in total one atom so far that belong to the plane. How about this atom? Is the entire atom located inside the plane? No, only quarter of the atom. This quarter of the atom is the only thing that is located inside, and the other, the 3/4 are outside the plane. The same thing for this atom, only quarter of this atom, only quarter of this atom F, only quarter of this atom D. So this gives 4/4 times 4 gives one more atom entirely, in total. So we do have 4/4 gives one atom and 2 halves gives one atom. So in total, we do have only 2 atoms who are completely, or 2 atoms. All of these fractions or parts of the atoms will form only 2 atoms that located inside the plane. So according to this definition of the planar density, it should equal to the number of atoms. So that's why we were counting how many atoms inside this plane. This should be on the top, and on the denominator we're gonna calculate the area of this plane. This plane, it is simply, and this is step 5. Step 5 is to calculate the area. This area, it is rectangular area. Has a length, and this is a tricky part. This is very important thing. Don't calculate the area from this figure. No, calculate it from the original unit cell. This area, it is rectangular area. So you should find the length of this edge times the length of this edge. What is the length of this vertical edge? It is A, very simple. How about the length of this edge? It will be A square root of 2, agree? Why? Because this edge is A, this edge is A, and this is gonna give us a triangular shape. So this is the hypotenuse of this triangle, so it will be A square root of 2. So if I ask you what is the area of this rectangular shape, the area will equal to A times A square root of 2. Which gonna give us A square square root of 2. This is the area. Then your objective is just to replace the A in terms of the atomic radius. For the Fcc crystal structure, we said that A for the Fcc crystal structure equal to square root of 2r. Plug this here, you're gonna end up with the area. So this is gonna give you the area of the 110 plane that belong to the Fcc crystal structure equals. How much? It will be 2 square root of 2r squared. So this is gonna give you 4 times 2. This is gonna give us 8r squared. This is the A squared times the square root of 2. Which gonna be this area that located in the denominator here. Then you're gonna just simplify, do some simplification, like removing this 2 with the 8, cancelling. This is gonna give us 4 in the denominator. So we're gonna end up with 1/4 square root of 2r squared. This is gonna give us the planar density for the plane 110 that belong to Fcc crystal structure. Again, this same plane for a BCC crystal structure will have a different planar density. So these linear densities, planar densities, it is important to know how do you calculate them. It is not clear so far to you the importance of these 2 measures or 2 quantities. You don't know what is the importance or the benefit of the linear density or the planar density yet, but we're gonna use it for the next chapters, and it's gonna be much more clear the benefit why we are explaining chapter 3, the calculation of these 2 quantities, because we're gonna use them for identifying the properties of the material and linking the material properties and features to the atomic structure. Make sense? So that's it for chapter 3 and today's video. The objective again, just for today's video, just to explain to you how we can define the crystallographic planes for all crystal systems, including even the hexagonal crystal system, which is has a special way of dealing with its crystallographic planes. Also, we explain the linear density and the planar density, how we can calculate it. All right, so that's it for today, and thank you so much, and see you in another video.